קודם כל משפט אחד בעברית, אני מאוד שמח להיות כאן, ותודה שבאתם. Okay, let's switch to the talk. It's many thanks to many people. Much of the later part of the talk is related to Jay Feinberg and his group. And it's based on several papers that we wrote recently about stick sleep and rupture processes in experimental work. Let's start. There are a few things that everybody accepts about earthquakes. Number one, it's a propagating event starting from nucleation and propagating in front along the fault. Number two, there is a major fault weakening manifested by stress drop. Number three, there is elastic energy release. The common concept is that the stress drop and the weakening is due to the transition from static friction to dynamic friction, which has been known quite well in experiments. And then it's been shown that it's velocity dependent and sleep dependent. That's accepted or let's say by many people. What I'm going to present today is that the weakening is not necessarily by the frictional process, but rather by fracturing and fragmentation in the front, in the tip of the earthquake, which is a small zone in the propagating structure. The frictional weakening is true, but it's only a secondary, not essential for the earthquake itself to occur. And as a result, the earthquake itself is a fracture propagating phenomenon rather than frictional process. Not that friction doesn't exist, but it's there. Versions of this were talked about. Amir Sagi is not here. When I talked with him in the last year or two about this concept, he said, "What's new? You're talking about this for the last 20 years," which is in a way true, but only at the very end I will show you why I moved from a friction church to the rupture church. Okay, this is the outline. First I'll give examples of two so-called impossible or puzzling earthquakes, and then I'll go some experimental description and a brief discussion. This is a project that we were doing in South Africa in the deep gold mine at depths of 3.6 kilometers more than 10 years ago. We worked there on an earthquake of magnitude, a zone of earthquake of magnitude 2.2 that occurred in 2004. And the basic idea to go to the mine was to see the rupture zone of a real earthquake in the focal depths. Usually we see either the surface rupture, which is not indicative of the energy processes, or we see by remote sensing by seismologists. There are quite many seismologists in the room. But direct observation, this is probably one of the very unique cases that this is possible. And I'll show you very briefly the structure of the rupture zone, the slip surfaces that we observed, the rock mechanics experiments that we ran on sample collected in situ and tested in the lab, and we did also in situ direct stress measurements in the fault zone and surrounding the fault zone. By the way, this is me, and this is the type of the field work in the 3.6 kilometer. Now, this was an ancient fault zone, strike slip primarily, that was active about 2 billion years ago. It was not inactive since the time and underwent significant cementation. What we found is multiple slip surfaces that we'll describe in a minute. It was recognized it's common practice in the mines to recognize slipping surfaces, but something which is called rock flour, kemach sela, which is a fine-grained sub-micron gouge, and the rocks are pulverized along this rupture zone. This is the way it looks like. What we see is two main rock type, cataclysite, which is ancient cemented gouge, and the quartzite, which is the background, and the slip is occurring. You see the rock flour at the contact between the two. And this is a cross-section. For scale, this is 10 meters that we constructed three-dimensionally in the different levels. Basically, the reddish parts here are the parts that are being, where we found this gouge, the fresh rock flour. We drilled more than 10 boreholes across the fault in the neighborhood. We were lucky, one thing important to note, it's typically to see the rupture zone at the contact between the quartzite and the cataclysite. This is in all the examples that we have seen, or in 95% of the cases, the slip occurs at the contact. We were lucky that we could, in the drilling, we took a sample that we found two samples that were actually the contact itself. So we could take a cylinder, squeeze it in rock mechanics slab. This is the fault, in blue is the epoxy that happened, and this is a close-up between the cataclysite and the quartzite, and like in the field, the rupture occurred at the contact between the two, and this is what we see in the field, and this is what we see in the lab. We also measured, this is a map of the geologic map. The green is the fault zone. This, don't pay attention to the red and blue. These are the tunnels of the mine. And the red dot, the black dots and the line there are boreholes. And we measure the stress in situ using breakouts in the boreholes that I'm not going to discuss, but it gave us a fairly good knowledge and consistent knowledge of the in situ stresses at the site of the rupture. Most of the rupture observations are in this region. This is the reason that we have quite many boreholes there. So, in a summary of the geom of the structure, what we see is the cross section. We see at least 3 major ruptures and maybe a 4th one. This is a map view, and the red arrow is the indication of the displacement that we could see in the mine. Maximum displacement was about 2.3 centimeters, so it's a small event. So let's integrate these features. Okay, we ran in the rock mechanics lab, we ran samples of the host rock, which is the quartzite, the cemented gouge, which is cemented over 2 billion years, and the samples that we drilled through the contact between the quartzite and the cataclysite. They are presented in a typical graph. This is peak strength as a function of confining pressure. In green is the host rock, in black is the cataclysite, and the purple is the contact between the two, the two samples that we have in the contact between the two. And it makes sense because they fall in between the two. These are the two samples that we ran. This is stress versus slip along the experimental sample up to 2 millimeters. And what we see This is the peak stress, and this is the residual stress. Now we come to implication of this. This is, in the upper right is the map that I showed you before. These circles indicate the calculated stresses on these segments for using the in situ stresses and the orientations of these segments with respect to the stresses that we measure. Note now these are the stresses on the slipping fault. It's very clear without specifically stating the numbers. It's much weaker than the strengths of the rocks that we measured in the lab for the same conditions. I'm not going to specify it now, but under the same condition. So here is the summary. The rupture was on a cemented healed zone. The measured peak and residual stresses is 3 to 4 times smaller than what the strength is 3 to 4 times larger than the measured stresses on the surfaces. So there is a stress deficiency here. So there is a major stress deficiency how this earthquake could occur. Some clues, we see the pulverized nano grain powder, and we calculated the dissipated energy from seismic data, which suggests that this is about a few megajoule per meter square, which is a typical energy for intact rocks. We'll come back to the explanation here. Another, very briefly, is the Kaikoura earthquake in New Zealand. I just, as an illustration, this is a very puzzling earthquake during which about 15 to 30 different segments. In our case, in South Africa, it was only 3 or 4 segments. Here, about 15 or 30. Some of them are thrust, some of them are strike slip, moving in the same event. This is a simulation of the slip parts moving from 5 seconds to a few hundred kilometers afterwards in 75 seconds, and the rupture propagated on the surface that you see as the inclinations of those different surfaces. So the slip simulation is possible on this complex system, but it's possible only if you take very weak fault. And note, obviously, that there's no direct data like we have in South Africa. Okay, so these are the field observations. Now let's look at experimental analysis. This is kind of historical notes. 2 of the fathers of rock mechanics experimentation, Bill Brace and Jim Byerly, did experiments in stick slip in which they took a sample of granite. It was so cut under high confining pressure. This is what they saw, rising, dropping in the experiments. And so there is a stage of interseismic stress buildup, nucleation, and a drop, weakening and drop in the experiment. Displacements are less than a millimeter in those events. So this similarity they published the paper, Stick Slip as a Mechanism of Earthquakes. Interestingly enough, even though it's very appealing, at least to me, and some other people, it was not adopted. In general, seismologists don't use that. What they do use, they use friction. And I'll come to the very end why friction is so popular. But the weakening is attributed to the dropping that I mentioned earlier, and there are quite many experimental work that done in experimental work and theoretical work and modeling, including myself. I talked about this. This is just an example using the rotary system that we have in Oklahoma. And basically, what we do in those experiments, we have a control slip looking for the steady state of the frictional stress. This is the way it's being done. And the velocity, the slip velocities are typically from fraction of a micron per second to few meters per second. Note that there is a steady state is a built-in boundary control velocity. Let's see what we see in the experiments. We envision that during an earthquake there are two weakening zones. If we look at the slip or at the velocity itself, we have a rupture front that typically move forward at velocities of a few kilometers per second. It could even reach super shear. And in the backside, there is a sliding surface in a large earthquake. There is a sliding surface where the velocity is on the order of a meter per second. It could be 3 meters per second. But that's a typical velocity. So what happens is this is moving at kilometers per second. When this is in a large earthquake, it's really far away propagating. The backside of the friction is still moving. It takes it to accumulate the meters of slip. It takes it more than a second. It could take even more. So typically, as I kept bouncing again and again, the weakening is attributed to the frictional weakening. Let's look how it looks experimentally. And we go back to the experiments of stick slip that were produced by the pioneering work of Brace and Byerly. This experiment is conducted differently. Number one, we have spontaneous slip that propagates fast. Number two, the events are small, typically up to 1 millimeter. A slip velocity is not very high. The acceleration and the propagation velocity is very high. So the acceleration is in the orders of kilometers per second squared. So it's very high velocity. This is from the experiments that we ran. And in order to monitor that, the rupture, we have a sample which is about 10 centimeter in circumference, 10 centimeter in diameter, and we have 10 3-component strain gauges. This is a technology that we learned from Jay Feinberg and his team. This is what we see how a stick slip is being monitored in this setting. Each curve here is the record in one strain gauge, and they are shifted just not to overlap each other. This is time in microseconds, so we have to record everything in 1 megahertz for each one of the sensors. So typically what we see, let's say the nucleation is here in the black curve. It's flat to begin with, then there is a stress drop, then a decay to a constant value. And then it propagates in both ways. This is a circular sample. It propagates in both ways, and this is what the arrow indicate. These two arrows indicate the propagation vector in the two directions. And what is typically, and we see it time and again in the next few slides, that once the rupture front propagates, there is a rise in the stress. This is the shear strain in this respect, and then there is a drop. There is a rise and drop, rise and drop. So this is done in quite many experiments of this nature in the last 20 years or so, with major contribution, as I mentioned, by Feinberg et al. This is a sample of curve that we got in the experiment. This is the nucleation, flat and drop. Then when we come to slow or relatively slow, we get the rise and the drop. In a critical velocity that we come very close to the Rayleigh wave speed, what we see, we have a rise and then cyclical motion. This is observed many times, and there is a reason for that I'll show you momentarily in fracture mechanics. So this is what is seen in a strain gauge, which is about 3 millimeters off the slipping fault. The velocity here is on the order of 1.3 kilometers per second in the experimental work. And once the velocity is very high, what we call super shear, it's above the shear wave velocity, then we see very abrupt drop without this cyclical behavior at the fault. Now let's look at some results from in a similar setting by Ilyas Wislicki, a recent student of Jay. They have a very they have very high resolution of the behavior of the fault that we do not have in our lab in Oklahoma. If the velocity of the rupture velocity is small, then about up to a quarter of the Rayleigh wave speed, they got this behavior. It shows as this is the rupture front, this is the strain gauge, and this is the rupture propagating from here to here, and that shows what the strain feels when the rupture approaches this position. Note that this is the intensity of the shear strain, and it's changing from extension to compression. This is the main point that I want to mention that. Now, this is when it reaches very close to the Rayleigh wave speed. Now, what is important here in this diagram, once they have all the experimental data, the black line in both graphs is the theoretical according to fracture mechanics that was established by many engineering work starting from Griffiths in 1920. So the experimental work fitting perfectly well to the theoretical fracture mechanics observations. And this is the most important component in this work for our purposes. So what's going on here? When you look at fracture mechanics, this is well known, going tens of years ago, backward. There is a singularity in the tip of the fracture. Once we assume a sharp tip. So materials in general, and rocks in particular, could not stand these high stresses. So there is a plastic zone or yielding zone around that. And this is an example here of there is a process zone or yielding zone, cohesive zone. There are many names for this. And the stresses here changes 1 over square root of r, of the distance from the tip. So they could reach singularity at the tip itself. Now, this singularity gives rise to the propagation and the breakage of the material. And this is well established in many works. Now, let's see what's going on at this fracture. This is based on a case of a tensor fracture in which there is, in fracture mechanics, in which there is extension, the fracture is being opened, energy is flowing to the tip to facilitate the breaking of the material. And turned out that if we look at shear fracture without friction, it's basically the same equations. The stresses is 1 over square root of the distance, and it's the same equation. This is a 3D plot of the calculated stress field at the close to the tip, and you see the rise of the stresses due to this singularity. Situation become more complicated when we deal with friction. This is the case here. Now, in terms of the stress field, there is only one difference. While here, because there is no contact between the two sides of the fracture, the stresses drop to 0 in the back side of the tip. When we have friction, they don't drop to 0, they drop to some residual strength. This is the strength of the friction. However, what is important is that there is singularity in the tip remains the same. That's related to the graph that to the previous slide that I showed previously about the calculations. This shows this is a shear with friction, and the stress field fit the theoretical, the expected stress field perfectly well. So even though there is a friction, the solution is the same for the stress field in here, but with the only difference is the residual stress in the back side of the friction. Okay, so we have seen that, and this is related to work that we did, we published some time ago, and we took the theoretical stresses and we emphasize here the cyclical nature, this cyclical nature. So what happens is there is a compression and then dilation and then compression. So, and we said what's going on here in terms of the propagating rupture. This is a schematic view. This is the intact rock. First it's undergoing dilation, or the other way around. Then it goes compression. So what you get a cyclical application of compression and extension on the sample at the tip. And this is a very rocks kind of a prima ballerina. They don't like too much stresses and too much strain rate. So what we suggested at the time, that this process leads to pulverization at the tip by breaking. The conditions, this is shown schematically. This shows the relative log velocity in meter per second, log. This is processes that we know. So this is a fault creep about centimeter per year. This is a earthquake slip of a meter per meter per second. This is the rupture front that at a few kilometers per second. This is meteorite impact, which is the other extreme of shock waves. Now let's, based on what one can calculate, this is shown schematically here. the strain rate and the stresses increase non-linearly here. And what we suggest is that there is a dynamic pulverization at the tip of the earthquake because of the very high stresses and strain rate. Strain rate is on the order of 10 to the 3 or 10 to the 4 per second, which is about 7 or 8 orders of magnitude more than in typical rock mechanics experiments. Now, this was tested by experimentally with a system which is called a Kolsky bar, which is applying shock waves, and this is what in our experiments that I showed a minute ago. This is the theoretical calculation showing the compressive stresses, the cyclical compressive stresses, and the strain rate. And I show you experiments by Ashley Griffith, who did these experiments in the Kolsky bar. When you apply on rocks this type of loading, particularly this cyclical behavior, that's what you get. It's not a surprise. It's just expected to get this type of shock application on the rocks. So what we've seen is the stick slip view. We saw the rupture dynamic, what's going on in the tip in terms of stress drop and so on, and showed you there are not many experiments done on the behavior of rocks under rupture, but they are very systematically showing the breaking of the fragmentation of the rocks. Okay, so now let's look at the efficiency. There is a weakening at the tip. There is a weakening by the friction. So both zones are indicate a weakening. So this is a compilation of several data sets. They include in red our observation in the PMMA, in the rotary shear. In black dots here are the experiments of with granites under high confining pressure of Brace and Byerly that I showed you in the historical data. And the graph itself shows the weakening, meaning this is zero weakening or almost zero weakening. This is total weakening. The rock has no strength. And this weakening factor is the ratio between the drop of the stress as normalized by the peak strength, the peak stress before failure. We need this normalization because we have here experiments done in normal stress of about 2 to 3 MPa to experiment done on high confining pressure of 100 MPa. So we need to normalize it to the normal stress. All these, and the weakening intensity is plotted as a function of the displacement. This is total weakening, and the associated slip, experimental slip, is on the order of less than a millimeter. So all of them show, as expected, some kind of a linear dependence. They reached about 60 to 70% total weakening, of the total weakening. And this is all set of different experimental settings. So what we see here is weakening by a stick slip front is about 60 or 70%. Some of the cases is over 90, is approaching 90% of the initial, of the peak strength in less than a millimeter of slip. What is the situation in a friction experiment? I will not show it here. I'll just tell you that in friction experiment, the weakening occurs at about between 2 to 5 meters. Some experiments, depending on the normal stress, it occurring at 10 meters of displacement. Similar weakening of 60 to 70% occurs at meter of displacement. So, I don't show it. If you have the time or question, I can show the graph. So the one thing we found is the front is much more efficient in getting weakening by orders of magnitude, not by displacement, but also by the dissipated energy. The dissipated energy in the tip is very small. The dissipated energy in the friction is very high. So, basically, who needs the friction? Who needs the frictional weakening in order to generate an earthquake? No need for that. That's what we suggest. And yeah, well, it's popular. I don't want to go into politics and elections, but things are popular even though they don't make sense. So why is it so popular? There are several reasons for that. Number two, experimentally it's relatively simple. And so quite many people do this experiment. Number two, I love to cite Tabor, one of the fathers of tribology, who said the friction is easy to measure, difficult to explain. So it's always something that you blame it without being specific about the mechanisms. Now, in general, any process that you have shear and normal stresses can be explained in terms of friction. And because in the tip or anywhere, you always have normal and shear stresses. This is the nature of the beast. So the result is that you can explain by friction any of the experiments that I described to you can be called friction. And some people do that. Then the friction law can be used for simulation, as I showed you for the New Zealand earthquake. It can be implemented in very nice simulations. Okay, let's look at the implication. This is if this concept is correct. This is the way that we envision the earthquake process from the nucleation to the end. There is local conditions which are very difficult to define. They're defined by pre-stress, strengths, pressure, stiffness. Now, in this stage, we get some local yielding. For whatever reason, we cannot know. This heterogeneity lead to failure. Now, we get local rupture from that site. And it could be very slow, and in this case it's going to be a slow rupture. I did not talk about it, but if the rupture is very slow, the weakening is slow. Or it could be very high, depending on the local conditions, and then we get some intense weakening. This is on the local scale. This is a scale of an earthquake of magnitude -4 or -5. This is about the size of the stick slip event in the experiments that I described to you. Now we go to the large scale, the regional scale. Here we already have a rupture propagating. And it all depends now on the amount of energy, because the friction, while the tip of the earthquake consumes very small amount of energy, the friction consumes huge amount of energy. About 90% plus is consumed by the friction, including heating and melting. So there is a need for energy, large energy. If there is a small amount of energy, there is a stable sleep and creep until more energy being consumed, and the small event will die. It will remain a small one. And then there is option of large amount of energy. This is not surprising. That leads to large earthquake because there is enough energy to be consumed. But this is the scale of the lab, and this is the field scale of the large earthquake. So let's look at the conclusion. The rupture front weakening is a function is proportional to the velocity, the rupture velocity. The more in super shear you get very high friction, very intense weakening. A stick slip seems to be the most appropriate model for analog for earthquakes. The weakening by the rupture front is more efficient than the friction, and the tiny in situ nucleation is essential for running the earthquake. And basically what we suggest is a nucleation depends on the local conditions, the strong stick slip. The fault zone is being fragmented at the rupture zone, and the energy controls how big the earthquake is going to be. And then I still have a debate. Jay Feinberg claims that even if you don't have weakening at all, there will be an earthquake. I'm not a fictional weakening, but I'm not convinced yet. You have to invite him to persuade you of that. Okay, that's it. Thank you very much. These are the people who worked with me on that, and thanks a lot. I'll take questions in Hebrew or English. Wow. Everything is clear. מאיר, כן.
מה שכאילו מבין, אתה מדבר עכשיו על תהליכים בקרקטי.
תהליכים?
בקרקטי, שזה
כן.
עובר קצת את העניין של הפריקשן. עכשיו, כשמסתכלים על העתק, אנחנו רואים שהמרכזים, המקדים הם לאורך המשטח של העתק עצמו, אין איזה ריכוז של רעידות דווקא בקרקטי. איך זה קשור? אולי שפשוט הילינג, ואז יש לך איזה סדק נתונים, איך זה הולך?
אני לא כל כך הבנתי, שאתה רואה when you see a fault, you see, you're talking about a single earthquake or multiple earthquakes?
Not the fault zone.
Yeah.
On the fault zone, you get many microcenters around the fault itself.
In a single earthquake, you have one. That's in the simplified version. Then it can grow or not grow. You can see multiple tiny events. If the energy is not there, then you will not see a big earthquake. The energy needs to be there, as I mentioned. But if you, otherwise, you will see multiple small earthquakes, magnitude going all the range. In the mines, they see earthquake as, because of resolution, to -5 or -6, no problem. But those small events don't mature if there's no energy. Now, the point you raise is correct, because these local conditions, the local conditions are, even in the lab, it's very difficult to ascertain those local conditions for the nucleation. Shachar Wirtzman, his father is sitting here. Oh, sorry. Shachar Wirtzman, who is now doing his PhD with Jay Feinberg, is working exactly on this issue of how to control the nucleation. So it's so by introducing an heterogeneity in the property of, actually the strengths, the local strengths on the fault. So on a large fault, you have many places like that. It's not practical. Even in the mine, we could not trace this tiny location without very high resolution.
So another one. If you mentioned about the corrective processes, what about the Baumgart or also the damage of the diminutions? Might be very relevant.
Yeah, that's, yeah. Well, Baumgart is related to what's going on in the plastic zone, but the damage in the surrounding, we did not deal with it. It's real. It's part of the question is whether it's related to the tip or to the slip. I don't have a very clear answer, but Vladimir and Yehuda Ben-Zion are working very intensively on the background damage. It's not including in this model. We focus only on the tip, what's going on with the tip. You know?
Thank you. It's a stimulating talk. I want to say something to Meir. Maybe his question about the granular. We see a very similar effect in the granular dynamics, where we see a stress drop upon the onset of motion, then a velocity strengthening, and we still see earthquakes. We still see sixth.
Oh,
Yeah.
you should tell me that.
Maybe we should talk.
Where is your office? Hello.
I have two comments. One is very often we don't see clouds, we don't see pulverized rock. Sometimes then, sometimes not.
You say in the field or in the?
Even if you look at Kobe rupture, you go to Shikoku Island, you look at the plane, you see no damage. So it's really like very, very sharp. And the other thing is that from seismology, the drop is very often 3 megapascal, 5, 10 would be very high. So 3, 5 is very small action.
Okay, thanks for the comment, because I didn't show. No, I don't have a slide of that. Let's answer the first one. The issue of where you look for the pulverization of the gouge formation and so on. This is an issue of where you look for it. This was the main reason. The main reason that we went to the 3.6 kilometer depth is to see how the rupture looks in the focal area. when you look at the surface, or very close to the surface, you see, years ago, I had a discussion with Jim Broom about that, and he said the upper few kilometers don't contribute to the energy of the earthquake. They just ride along, everything comes from below. So if you want to understand, you have to go to below, or you have to go to places where it was exposed, like parts of the San Andreas fault. So in this respect, your point is well taken in the sense that the question is where you see it. Number two, it could happen, for example, if the fault zone itself is not brittle, let's say shaly, etc., cumulative over a period of time, the fragmentation is typical of brittle rocks will not happen. Nonetheless, the stresses will be high, but not. Secondly, what you mentioned about, I don't have the slide here, but it appears in the paper, in that paper of Chen and et al. You're absolutely right. The stress drop of earthquake going from -8, meaning experimental work, to magnitude 8 over 16 orders of magnitude is in the range of 3 to 10. What we say, it's 3 to 10 because it's determined by the tip. The friction, you get large displacement if you have in a large region a lot of energy. But small earthquake and big earthquake have the same front. This is where the radiation is coming from. This is where the stress drop is coming. And this is the reason we see the same stress drop over 16 orders of magnitude of earthquakes. This is one of the points that we raise as application of this model.
Before you put the nails in the coffin, of friction, this is almost a religion, the friction.
Yeah, this is the church.
You have to be careful.
I know.
Because the big gurus about...
Tell me about that. Well, I belong to that. I got this big machine I gave here some talks about the friction and so on. So I'm converted. What can I do? You also converted. No?
Okay, thank you. Thank you very much.